Hello everyone. So this is the first discussion meeting we are going to have on one very important topic, which is the Shockwave method. The Shockwave method is very important in calculating the butterfly velocity, which our main task is to calculate the butterfly velocity. We earlier used a different method, which was the entanglement wedge method that we successfully used and found that in our case the holographic QCD model, which is when we take the magnetic field out of the context, make it zero, then we found that the butterfly velocity was a function of chemical potential. So as we are increasing the chemical potential, the butterfly velocity is slowly decreasing, and there comes a point when it turns to zero. That I think is very important point, but we haven't thought about it yet. But okay, leaving that aside, today we are going to start with you just touch it. We're going to start with the Shockwave method. So let's give a brief overview from where I have taken the literature, because literature is very important, and for all you guys who are going to read about it, the literature is important. So I am the first most important literature is a paper I have been writing on the paper. So it's a review article by Victor. The title is itself very interesting because it's related to holographic chaos. It's recent developments in the this is basically a review article, and its DOI is 10.1155. Okay, so this basically this article is a review article by Victor. He is presently a postdoc at GIST Korea, South Korea, and in this review article he has mentioned all the different techniques which are currently used in the description of holographic quantum chaos, ranging from this. Let me go over it. Ranging from the brief overview of chaos and holography in classical context, and he goes over to this holographic setup where he goes on to describe the details of the TFE thermofield of double states and its corresponding two-sided black holes. Then he covers a bit in short of the entanglement wedge method, which we use but in a different setting. Then he also covers the Shockwave method that we are going to talk about, and he tells about the stringy corrections as well, and the different bounds that we have in our holographic setup, ranging from for the Lyapunov dimasses bound, and for the butterfly velocity, like so many bounds, but most important is the Lieb-Robinson, the holographic part of it, the holographic part of the Lieb-Robinson bound that we are going to talk about. So this is a very important paper, and I ask all of you guys to go through it because it gives a nice review of all the things that we are going to cover in our research, basically to determine the butterfly velocity from different methods. So today's and the second most important literature that we are going to use is basically it's a doctoral thesis. It's a doctoral thesis by Mr. Wong, Dr. Wong. Sorry, no, it's a Dr. Wong. So Dr. Indian Wong, and Victor is also doctor, so I should show some respect. Okay, Dr. Indian Wong, and the title is the title of the thesis is Entanglement, Chaos, and Causality in holography. If you need the link, I'm also sharing the link. The link is and the links of both these papers and other corresponding papers will also, since this talk is for the first time we are giving online flavor to our discussion meetings, so that other members who are not present here can also see and post their comments. So all the links for the corresponding literature and the relevant papers will also be put online, and any questions you can also put there in comments. So let's start with today's topic, which is the Shockwave method. So earlier we described the wedge method, which was a different method. It's physically drastically different method as compared to the entanglement wedge method that Nikesh talked about. But surprisingly, both of them give similar results. That's why I think the title of one of Wang's paper was A Tale of Two Butterflies. So because they use both these methods, and the answers that came out of butterfly velocity were exactly the same, basically. So we have two identical CFTs, and they are called thermophile double of each other, because one CFT and there's one other more CFT, and they are double of each other. They are basically identical twins. CFT, and the details can be read in the paper. Basically, we are calling them thermophile double state, which are dual to a double-sided black hole.
Identical means?
You can read from this paper. Nikesh will talk about it. I have gone through just from the brief perspective of it. I have not gone into details, so I still don't know the details of it, but I am still trying to learn. So let me see what is this thermophile double. Okay, so basically what we are saying, I am reading from the chapter 2 of this thesis. So they are saying that, so basically we have a thermophile double state, details will be covered by Nikesh, and this thermophile double state is dual to a two-sided d+1 dimensional planar black hole. Okay, it's a dual black hole d+1 dimension, and on the boundary you have a thermophile double state, which basically is two CFTs, which are
like a single CFT but two boundaries, the left boundary and the right boundary.
Yeah, it's like a single CFT but with two boundaries. Like there's a left boundary of the CFT and a right boundary, basically a CFT which has double boundary, and its corresponding in the bulk is a dual-sided black hole, which is a planar black hole, and it is in d+1 dimension, because boundary is d1 dimension, then the bulk will be a d+1 dimension. Okay, so what we do, we basically do a perturbation. So what is basically I have just read from the rough idea is that you provide a perturbation in the boundary. The perturbation is provided in the boundary, and what happens, the perturbation as it grows from the boundary to bulk. So you have a boundary which is a thermophile double state, you provide perturbation there, then you let the perturbation go from that boundary to bulk. So as the perturbation goes from the boundary to bulk, you will create a back reaction to the geometry. Geometry will have a back reaction to it, and that back reaction in the horizon, near horizon, can be understood from the shock wave analysis. Okay, so that shock wave, that back reaction in the geometry, what the back reaction of the geometry can be understood from the shock wave analysis of the near horizon metric. Basically, so that is the basically the crux of this method to the shock wave, and the back reaction of the geometry is somehow connected to the shock wave of the near horizon, and that shock wave analysis is going to give us somehow the butterfly velocity, and how it is going to give us the details of it will be covered in two parts. So today the first part will be covered by Nikesh, who will give you the idea how it is connected, that how these thermofield double states and how the OTOC comes into picture, and how basically we are going to do the calculations. So if you guys have any questions, even a minute question, you're all welcome to post the questions here. And those who are online, those who are not present here, they can also post questions in the comments, and we'll try to get back to you as fast as we can, because questions are very important, and all those questions will be very essential to your and as well as our understanding as well, because questions are basically the key of the research. So without further ado, let me invite Nikesh to the stage, and he will start with basically the whole shockwave analysis, and he will tell us about the use of OTOCs and how they are being used and the details of it. So Nikesh.
Okay, so first a very honest disclaimer. The study of OTOCs in holography and in the context that we are using is physically very intensive to understand. So I'm making progress towards understanding it completely. Today's part more so will be a little bit you will feel that some of the pieces are missing, and hopefully from this discussion and in the next part, by the next part, we have the complete story. Okay, so okay, I'll maybe start this way. A little bit physical intuition about how to understand this OTOC. Suppose I have a spin system, spin chain, and there are several of them. Maybe I'll draw a couple more. Suppose at time equal to 0, we prepare our system in such a way that only these two spins are entangled with each other. Is it visible? Not visible, sorry. Okay. Yeah, so only these two spins are entangled, and there is interaction in the system, but only at t equal to 0, only these are entangled. Okay, so when we evolve the system, the unitary evolve the system, with time, due to the interaction between these spins, what will happen is that suppose at some later time t0, this system will be sort of in a following state. And so on. What has happened is, initially I had these two spins entangled. As a unitary evolve this system, this entanglement spreads through the system. Suppose at a certain time t equal to 1, of course this is not a process that will happen instantaneously throughout the system, it will propagate. So what will happen is that at a certain time the neighboring spins will be affected, then even further spins will be affected, and so on and on. Okay, so this is what we call as entanglement is spreading. Now when we look at this state,
Entanglement is spread. Normally we know that entanglement between two particles or between system to subsystem and all. So here you are saying that the subsystem is growing or the entanglement is growing?
Entanglement is growing.
How
the system?
The subsystems are fixed?
Yeah, system is fixed, yeah. Subsystem is fixed. Entanglement is growing, we can physically understand, because there is interaction between these spins. If there would have not been
the interaction between the two spins.
Yes.
Then it will be between.
No. Interaction and entanglement is different. Entanglement is the information or the state of one will affect the state of the other.
Yeah.
Interaction is a different thing.
Yeah. That's what I am asking. Here, if there are two spins, you
Yes.
know the property of one particle, and then you will know the property of the another
Yes.
particle. Like the entanglement spread, the four will. Can the four spin will be entangled?
Yes. That's what I mean by entanglement spreading. More and more
so
spins
change
will
in
get.
one property will affect the other.
Yes, exactly. So when we call scrambling, like the information is spreading or is getting scrambled, like physically what this means is like now in this state, you are in a very like you cannot looking at this, you cannot retain the information about the initial system that I had, and that initial information is that the two particles are entangled and the rest are not. Looking at this system, I cannot. Like you would say, okay, I use the unitary time evolution. I can always like back evolve and find the information. But as far as I understand, when this system reaches a chaotic state, it can the system becomes basically non-integrable, and we cannot back evolve and retain the information. So this is a physical intuition. I think this intuition helps a lot in understanding what we will try to do in the Shockwave method.
So if the system is non-integrable, we cannot do the reverse.
Yeah, that's what non-integrability means. Like we cannot, like if you have to back evolve, I have to integrate the unitary evolution.
So what you're saying is the system is initially integrable. So
Yeah.
for some initial condition, initial time, we can easily do the reverse unitary transformation.
Yes.
And find initial, but after some time,
Yes. Like
like-
information gets scrambled.
okay,
You
is there
cannot-
a specific time?
Yes, scrambling time.
scrambling time. I think that's
Okay.
that's how they define the scrambling.
Okay.
He is going to talk about it.
Okay.
Okay, so like having this picture in mind, of course, this example was for like two entangled spins. I would replace this with a perturbation that I act on the system, and then we will, very analogous to how entanglement spread, like the notion in Shockwave is that the perturbation will spread in throughout the system. Like having this physical picture in mind, I think helps a lot. Okay, so this lecture, like this part may not be that coherent, like I haven't prepared it that well, but let's see how this goes.
It can be as casual as you want. It's
Yeah.
just a discussion
Yeah.
meeting, so everyone will have questions, and by questions we'll learn.
Yeah. Okay, so how? Okay, so maybe I will write what OT is. So for large n gauge theories, like one can find that the OTOC, which we define as this 4-point function, this 4-point function, like one can prove that for 4 large n gauge series, like we are totally at the boundary, we haven't yet invoked any bulk notion or anything. Like for this we can prove, and this result has been discussed previously as well in our discussions, which is simply given as t star x upon vv. Okay, so as we know, this is the Lyapunov exponent, this is the scrambling time, and vv is the butterfly velocity, and x is the spatial separation of the operators. Like suppose this is my boundary, I perturb the system at this x equal to 0, and then like I use w as my perturbation operator, and suppose at a certain spatial distance x I want to make a measurement, so I use v as my probe operator. So this is my probe, this is my perturbation. So like now that the physical picture that I gave, suppose I make a perturbation using this operator w, and this perturbation will be on a certain state. In our case, that state will be the state that we have mentioned, the thermo double state. I'll come to what thermo double state is. So I have I will induce a perturbation here, and as we saw for entanglement, the entanglement spreads throughout the system. The perturbation will also spread throughout the system, and like I said, it is a non-local process. Of course, it will suppose at a certain spatial distance x, that spreading of information like that. Suppose like I have some time, let's say t1. By the time t1, the information of the system has, let's say, only reached till this spatial part, this part, which I maybe call it as x1. So basically, when I use my probe operator here, like after making the perturbation at time equal to t equal to t1, I'm not going to probe anything because information has not reached here, right? So OTOC is basically a measure, like it will quantify the amount of information that is reaching at a certain spatial point that we are concerned with. Now, if you are at t equal to t1, since the information has not reached till here, this OTOC, like the 4-point function will give me a 0 value. There is non-zero overlap. Let's say for a certain time t equal say t star, the information we have waited enough time. So now the information has reached the spatial point that we are concerned with, and now OTOC will give me some non-zero value, and I think that's how is the scrambling time, like the time up to which at a certain point now I have the information about the system. Like more precisely, when the order of this OTOC becomes 1. Like basically it's saying that now it has some non-zero overlap. We define that region as the size of the operator.
Like even in the in OS lecture, he was talking about the overlap thing.
Yeah.
So when the overlap starts from the point, that's called the scrambling time basically. So I think Jasper, is your question clear?
So scrambling, like this operator is our choice, right? V of x.
Yeah, it is our choice. Yeah.
So according to what x we choose,
yes,
we will have different scrambling time.
Yeah, that's what I think that is for a fixed spatial. That's why I think we had this discussion of butterfly velocity and the Lobnow exponent being one being space-based, one being time-based. I think this is what it has to do with
Fixed space.
I think so.
Yeah, when we are calculating the butterfly velocity, we are working in that fixed space region.
So how much distance then? And what distance are we supposed to fix it?
No, like that does not depend. We could choose any as we'll see. I think the profile that we'll look at will have this x dependence. We are not fixing any distance. We are just saying okay at any x. I mean,
we are doing a spatial analysis basically.
For different x, so there will be different scrambling time.
Yeah.
So it's like you will just put it like a function, right? Nothing.
Because he is saying that at particular x, if the
No, actually, what happens is if we will have to choose our time. Like if we do it a bit earlier in time, then we'll have more scrambling compared.
Yeah, like I will go like a future. I will label my time in future because the past thing is like a little bit different.
Okay.
So I will say later and later time.
So you
like
are going to okay. Because in their literature they are saying
they have used
okay.
That's a little confusing, but it's exactly equivalent to using the future labels.
Scrambling time was like over entire system when like perturbation reached. So it should not depend on x value, right?
Yeah, it should not depend on x value. Yeah, you're right. But the time on which we start will depend, like how much it has scrambled. So the butterfly velocity will take. Like, am I right or?
Yeah.
Because if we start from like they say that if we start from earlier time, then like when it saturates from the T star, then the amount of time basically the cone that you have.
Yes.
So the scrambling will be more.
Yes.
Okay, yeah.
Okay, so I have one more question. Okay, let's relate it to the spin system.
Yes.
Let's say we have no spin system, and so you have just said the scrambling time. Till that time, we can do inverse transformation and get back to our initial condition.
Right.
Now if we come back here, as we have the freedom to choose this x, of course, once we choose it, we'll fix it.
Yeah, I get it now. Like both notions do not have anything to do with each other, right? That's what you see here.
Also, the operators are initially commuting, so in a spatial picture, they will be apart, like they will not be close to each other. But you will have an initial overlap if you put them real close to each other.
Yeah, okay, fine, that is fine. But I have a choice, right, where I can.
Yeah, you have a choice.
So if I have a choice, then I can like practically define what's my scrambling time. And if the scrambling time is the time where I can still do my reverse unit transformation, like it's still integrable the system.
So yeah, you cannot call that a scrambling as such.
That won't be like called scrambling.
As far as like I understand, scrambling means that like it becomes it becomes chaotic. Like when it becomes chaotic, then it is not integrable.
Scrambling is
it's not chaos.
Like okay, if we go by Neil's paper, like scrambling is a necessary but not a sufficient condition for chaos.
Yeah.
So we cannot call all scrambling as chaos.
Yeah.
But since we are like as Victor said, since we are dealing with holography and black holes are dual to it, so and they are the fastest scramblers. So here in our case, we are denoting scrambling as a form of chaos, just for this special case in holography.
Okay, so maybe that means like once, like any point we choose and the information reaches there, I think it is chaotic, in a chaotic state, because then we cannot, even though we are calling it as scrambling, but as we have said, black hole, it is dual to the black holes that are fastest scramblers. I think that's why the scrambling time, like if we go like do the backward unitary evolution, I think we'll not get back information because it is also chaotic.
Once the system gets non-integrable or chaotic, you can't go back basically, because you don't know from where it started.
Like any corrections from anyone who has like worked on
scrambling time is like when perturbation reached over entire system, right?
No, I don't think so. Because then, how do you define the size of the system? I have infinite, so like it will keep traveling for infinite time, right? I don't think it's the entire system. I think with the point at which we are caring about, at the time that it has taken to reach that, I think that's scrambling time. I might be wrong.
No, we'll check about it.
Yeah.
So you can continue.
I think he's a bit off, because then we can ask the question: how big is the system?
I think when the entanglement gets maximum or the entropy becomes maximum, that's the scrambling time. Like you measure the time till your entropy reaches a maximum.
Yeah, in terms of entropy, you can define that.
But like the way the scrambling time is defined is that when this OTOC becomes order 1, meaning that there is some non-zero overlap, and like only non-zero overlap will be only that when this probe operator has something to probe, like when the information has spread enough to this enough so that this region can probe. So when it probes, I have a non-zero value for my OTOC. That's how they define the scrambling time. When this
O1 becomes 1, see, because what was that? A commutator or correlator? This is commutator, right?
Yeah, this is commutator, but like it is related.
Okay.
There will be some.
And the correlator will have the exponential part.
Sorry, I shouldn't be saying OTOC. I think commutator. Like when the commutator is of order 1, that's the scrambling time.
OTOC can be said of commutator as well. C is for commutator and correlator both. So you have to differentiate that sometimes. Yeah. Okay.
Only like there is a non-interesting ordered part as well. So
Okay.
So basically, when this commutator reaches order 1, we also define that as the size of this operator W, because now like this x value will tell me like due to this perturbation how much the information due to this perturbation has spread in the system. So like at certain time this will be the size. Like at every time there's a specific size of this operator. So whenever there's this non-zero overlap, when it becomes order 1, we call that as the size of the operator W. And the rate at which basically this size increases, that's what our butterfly velocity is. Yeah. Yeah, okay. So just one more comment, like before going into the bulk calculations. This is a purely boundary calculation. We have seen this is for large and gauge theory. So this is purely boundary. As we move forward, when we'll calculate the profile of the Shockwave, which I'll call, okay, let's say h of x, this profile will take exactly this form. Okay, and like just that instead of t star we'll have some other quantity, instead of lambda we'll have some other quantity, instead of vb we'll have some other quantity. We'll basically just compare this boundary result with that Shockwave profile and calculate our vb, lambda and t star.
Oh. So this is calculated from purely quantum
Yeah,
mechanical?
purely boundary, yeah, purely CFT result.
Why are we taking large n?
Large n, I think because whatever we talk about these dual theories, like all this, it is for these large and gauge theories. I think that's for this duality lies.
We're not talking about dual here, we're just talking about CFT side. So why not for?
Yeah, because in our mind we know, like we are now going to use the bulk approach. So we
relate to the bulk.
Yeah, so yeah, that's basically means.
So do we know what kind of form do we take in, like small and gauge series?
There might be. I'm honestly not sure about that.
N is the
And I
degree of
think even
N is the
this-
degree of freedom, right?
N?
Capital N is the degree of freedom, or
I'm sorry, which N?
for large N.
Yeah, N. The degrees of freedom. Or the color you can see.
So I think Jasper is going to work with
Flavor.
even more M because he is going to now apply flavors.
No. Professor was talking about like the ratio, color and flavor ratio nearly to 1.
Oh.
So
It's a
doesn't
special.
necessarily
It's like an improved holographic QCD. Like
I have no idea.
Yeah, like basically for large N gauge series you can also relate N with the central charge and goes like N square. The central charge.
Okay.
Okay. So that was butterfly velocity. I think it's clear from
Yeah.
this. Now moving on to the Shockwave method. Okay, now maybe let me say a few words about this thermo double state that we have.
नहीं वो नहीं मैं एंगल ले रहा था ना उससे तो बैठ अच्छा तुम बैठ वहीं बैठ गया इसको भी कट करना पड़ेगा
And I think understanding like thermodouble state is, you could just understand it as some state, but like the things that I'm going to say as proceedings to this will help to connect OTOC and the Shockwave profile. Like from the equation it will be pretty evident since they take the same form, but like physically what's happening.
Still, what do you mean by software profile?
Profile, it's a function, right? It will not be some constant, like it will change with the coordinate values. Yeah, so it will depend on the coordinate x. That profile means that's the function that the Shockwave will attain.
When you start, I think you will get to know because it comes after you define your geometry in critical coordinates, and then when you disturb it because of the perturbation, then the Shockwave comes into picture, and basically from there you can understand it.
Okay, so thermodouble field state is like defined as linear combination of these eigenstates tensor producted, like of course some coefficients. Like this is the original system and this is the copied system, and we are tensor producting to call this a thermodouble state. Now I do not know physically what does this mean. I'll be honest here. But like we
Basically,
could,
I think
for all,
in the name it's like they are two thermal fields,
yeah.
and they are basically double of each other maybe.
Yeah, because your tensor producting, I think that's why the
So
double
the thermal
name.
field double, that's it.
You extended your Hilbert space, I think.
Yeah.
This is what we do when we have to like purify the quantum states in information theory. We extend the Hilbert space, so I think that's what that is. That's also called thermofield dynamics. So
Oh yeah. Because of the extension, yeah, we need to extend it.
Can you little elaborate a bit?
Like okay.
like if we want to solve the master equation, we need like a pure quantum state. But let's say our quantum states are not pure. Then we extend the Hilbert space, and like say the left part will only count the terms which are like of type 1, and right side will be like of type 2.
Yeah.
And we can do the dynamics like this, and at the end we can just use the detanglement theorem to get the final result. That's what we do there.
Okay, that's why we have a double system too.
Yeah.
Oh, okay.
And the name is also similar, like
Yeah.
thermofield dynamics and thermodouble state.
Yeah. So we need to also read that literature, because if there's connected, there might be some ideas that we can have from those quantum information theories.
Yeah.
Maybe
So there is just some state in the CFT, which I'll denote this as TFT, thermofield double. So I'll define a state, let's say phi. What I do is I take my CFT state, I act with the perturbation at time 0 at origin, like space and time is like very important here, and then I want to probe it at certain spatial point x and at certain time t. So this is the state that I prepare from my initial CFT state. I do these two operations. Then what I do is I define another state psi prime. In this, what I do is I first probe it and then add a perturbation. So like if you recall the expression for the commutator that we had, it goes like, yeah, so like if we recall the expression for the commutator, it goes like omega 00 vxt expectation. So this 4-point function that we have, so we could understand this commutator as simply the overlap between these two states that I've prepared. Okay, so like see, this commutator can also be understood as the overlap between these two states that I have written. Like writing it this way will make the contact between OTOC in the boundary and the Shockwave profile in the bulk. So that's why I've just mentioned this. Okay, now all the machinery is ready, like the bulk boundary machinery is ready, like how we will go back and forth between things, like what OTOC means in the boundary. We just somehow briefly discussed that the shockwave, something that we are calling as a shockwave, will correspond to OTC. So we have talked a little bit about OTC, and now the protagonist of this entire discussion is this shockwave. So our next goal will be to go into the bulk and compute this shockwave profile. So okay, so the very first thing that we should do when we are doing this shockwave analysis is that adopt the Kruskal coordinates. We call it as a Kruskal extension. Why we adopt this extension is because we will do analysis along the horizon, because the shock wave, as I will discuss, will be created along the horizon. So whatever analysis I want to do is along the horizon, and to carry over analysis smoothly over the horizon, crustal extension will help me. That's why we choose crustal extension. So maybe I'll write down R metric itself. ds square is, I take the radius length to be 1. So this will be g is the ds square. So this is our metric. Hopefully I haven't done any mistake here. There's an exponential. Okay. I've written this correctly, right?
Yeah.
Okay. Yeah. So basically, this part, as I said, we have set b equal to 0 to get this part as the isotropic part, which also makes this a metric of a planar black hole. Okay. So firstly,
But planar in what sense?
planar in the sense that the horizon will lie in a plane.
When you
When
go z
these
tends to
are-
0, when z tends to 0, right? Basically, the asymptotic radius.
No, not in the boundary. Near the horizon. Horizon black hole.
Okay, near the horizon. Okay. Near the horizon, you want to make it plane.
The horizon lies in a plane.
In a
That's
plane.
what we mean
Okay.
by planar black
Okay.
hole. And that happens from the metric. We can read it off when this dxi part is isotropic. We don't have. Suppose if b not equal to 0, we have a certain coefficient for dx2, dx3, so that makes it non-planar. Okay, so the very first step would be to get rid of this z in the denominator. The first thing that I do to my metric is do this transformation. Define a new coordinate, which is the inverse of z. So this will give me e to the power minus 2a by r square times r square minus g of r dt square dr minus r to the power 4. So r to the power 4 dr square by gz. And this part will remain as it is.
That will be gr.
dr square by
Because you are going-
sorry, gr. That's right.
dr square by r4.
Because it's r square in the denominator.
Oh, okay. Sorry. So I'll basically just use the example of R metric itself, because anyways I have to give the sample of how to go about in this method, so I'll just use R metric. So this is the key step is going to be this crustal extension, the very key step. This is the thing that I took a little bit time to figure out how to exactly do it for R metric.
Okay.
So okay, this is okay. Maybe I'll just continue here. So this is the result that we have now. Like we usually do in the crustal extension, we have something like a of uv times du dv and terms. So I basically want to rearrange these terms in such a way. So the time and the radial part in such a way that I can express this part as a product of these two coordinates u and v. That's how the usual crustal extension goes. So that's my next aim to do. So what I'll do is I'll simply take this r square and multiply it throughout inside. So this is r square. This r square goes away, and this r square. So now I can see that the coefficient of dt square and dr square, these functions are inverse of each other. So the very natural thought that will come to the mind to make it of this form is to do the tortoise transformation.
Okay.
So dr star dr f of r, where I define my f of r as r square g of r. Okay. Now, unfortunately, like for most of the cases that people have used this method for, this is not an integrable thing. So, but thankfully in the analysis, as I said, we are going to be concerned only along the horizon. So what we'll do is we'll approximate this function using the Taylor expansion, and we'll just keep it to the first order near horizon. Like I'll expand it around RH. That will
be a non-integrable system. What will be the like we want on? If there will be integrable system, we will back to the initial state.
No, that's just totally disconnected to what I'm here doing. Like non-integrable in the sense this is non-integrable. This.
Oh, in terms of integration.
Yeah. In that sense, I was saying the unitary time evolution cannot be. Okay, so. Yeah, so.
And just one more question, like, is there a physical significance for using the tortoise coordinate, or is it
just to no physical, just to bring it into this form. I made the Kruskal extension.
Okay, so it's a mathematical choice that you are imposing on it.
The Kruskal extension, physically, I want to go smoothly along the horizon.
Okay.
That's why I'm choosing this Kruskal.
Okay.
It's the best coordinates for that. To bring it into that form, I'm further doing tortoise transformation, because now I have this function and this function which are similar. Like they are not two different functions.
Yeah.
Or even if they would have been different, we could have done tortoise in a slightly different way, like by taking square root of f of r.
Choose our dr star in such a way that it will. Okay.
The aim is to bring it in this form. That's why it's tortoise. Okay.
Give us a final result.
Like, yeah.
Like the final result?
You want to?
Yeah, your final metric in Kruskal coordinate.
Yeah. He's saying basically instead of doing the in between steps, because this is just maths, you can just write the final metric that you get in Kruskal.
Right. So I'll do that. So basically, when we take a metric and do the tortoise transformation, I get my final Kruskal form as follows: h of r of mu b times r of mu b whole square divided by alpha square uv. That's my first bit. It's du dv e to the power minus 2a divided by r of mu v square r of mu v square dxi. So yeah, this is
alpha come into the picture.
So I will define alpha. Alpha is basically 2 pi times my Hawking temperature T. So like you will be wondering how this alpha came into picture. So that basically comes from this is the Kruskal extension that I used, or like generally is used. T star minus r, and V basically same thing with plus. So this is exponentiated.
Yeah, it's e to the power.
Yeah. Generally, like when we do Kruskal extension for Schwarzschild, we like just simply take a linear form, u equal to T star minus r and Vs. But here we are like going for the exponential choice. Aim is just to get it into this form, and I have it in this form right now. Du dv, this auv is this entire thing here, plus some buv, which is this.
But you have defined your tortoise coordinate in r star.
Yeah. I'm coming to that.
So your t star, how come?
Oh, sorry. R star. Yeah, that's what happened. R star. Sorry. T minus R star. Okay. So this h of mine is this. H of r is defined as r minus 2a r square. G of r. This is my h of r, and I think I've mentioned everything else. Yeah. Basically, my g of r times the exponential factor.
So
that I
just
have.
one question here, like, so basically you are doing the shockwave analysis,
Yes.
and you have changed the metric into cruscal.
Yes.
So when you are doing the shockwave analysis, what's this significance of this h of r there? Like, what is it doing? Like, what is it telling you?
So far, there is no shockwave.
Okay.
I'm just playing around with the initial geometry that I have. I'm not playing around with the geometry, with the coordinates. Metric always has two informations, one of the coordinate system and the geometry. Geometry is still the same, coordinates has changed. So far, no shockwave.
Okay.
This is just for like.
You
I did not want to write this
you
entire.
have to introduce it, so you can use it like
Later, because these two pieces are going to be the most important thing.
Okay.
I'm just lazy to write it again and again. So like writing exponential will look ugly. So just define a new
Yeah.
edge.
Okay.
Okay. So now, like if you see that U has this R star dependence, the tortoise dependence, and I have not put R star anywhere there. I've just kept it in the initial R only. The step would be you like one can. Like I had this equation dr divided by r square g of r. This is what I had, the tortoise transformation that I did. Now from here, what I could do is find r star as a function of r, then invert it, which is not going to be possible, which was already it is not integrable, and like, even if I do Taylor expansion and integrate, it's not invertible still.
Yeah.
So the best thing is to just do the transformation. I have r star. One very good thing of defining my the cruscal transformation in this way instead of linear form is that now if I multiply u and v, if I multiply u and v, I just simply get alpha r star. That's it. And what I can do is I can calculate r star as a function of r from this. R star is a function of r from this. Substitute this r star here. I have my relation r as a function of u and v from here. I do not have to do this thing twice. I can do a smart work and like just do this.
Okay.
And it will turn out that the relation, like in this relation will be a lot simpler. Like very easily I can invert it from here. So I've not. That's why I've just kept it r. I've not changed it to the tortoise, even though the transformation comes from tortoise. Okay. So like, should we do?
I think we should not fully finish it. Like, let's make it a two-part, because I think the time is also going a bit.
Okay. I think we'll stop here.
We'll stop here, I think, and the second part will continue from here.
Yes.
And also there are some gaps left,
Yes.
like we didn't draw the Penrose diagram and how it basically the perturbation.
Yeah, basically I would have talked about it next.
Okay.
Because I still haven't come on to crystal and sorry, shockwave.
Shockwave.
I'm just playing around with coordinates. Okay, then we'll stop.
So it will. So the plan. Just write down the plan for the next talk. Like what we'll do.
Discuss the Penrose. Penrose diagram. Compute the Shockwave profile. Compare BB. This should be the general plan for the next.
So let's give a big round of applause for Nikesh. And the questions that were raised. Okay, so let's. Who raised what question? Like you had some question, right? In the starting
about that choice of
scrambling time. Yeah, why scrambling time? And Siddhi has some question like what? You asked some questions, good questions like in the starting. I think we'll recheck the video and then we'll see. And yeah, you had one question about that in the starting, the scrambling time, and why does it matter? In the starting, you had a question about why the butterfly velocity is special and temporal. Is it clear now?
हाँ वो clear है. बताया था.
And I think you are going to work with Krylov.
velocity.
So I think it is a bit related to scrambling and much more sensitive tool of scrambling. So I think after this this part of Shockwave is over, we can jump on to the Krylov and discuss some bits of it. Okay.
Is that Penrose diagram going like the discussion is it going to be like including perturbation or before perturbation?
Both.
Oh, that's nice.
Okay. So this was the first part of our discussion on the Shockwave method, by which we are going to basically find the butterfly velocity. And earlier we used a Tag-element fetch method. So this was a part 1, and soon we will be having a part 2 of this method as well. And all those who are watching this on your laptop or computer, so if you have any questions, basically you can just drop in the comments, and the more the questions, the more better will be our understanding. And all this video is also be put in some groups, so all the group members are requested. So if you have any questions, just please do tell us, and the doubts, if you have any, and more references or literature if you have regarding to the Shockwave method or OTOCs in general, please do share up it. And thank you all for joining us, and soon we will have the next part. Thank you.